Okay, so we're on to the second respiratory challenge. The objectives are the same as the previous lecture. This time we're going to talk about pulmonary vascular pressure. And so due to the increased cardiac output that occurs during exercise, that leads to an increase in blood flow through the pulmonary circuit. This leads to an increase in pressure. And ultimately we need to minimize this vascular pressure for a variety of reasons. One of which could be, you could think of vessel damage, and then another one is edema formation. Okay, so if you remember back to basic physiology, we talked about Starling Forces, and so that's the movement of fluid in and out of the bloodstream, specifically in the capillaries. And so when we have greater pressure, we have greater amount of fluid leaving the capillaries, and this is something that occurs during exercise. Now, not only during exercise, but at rest, we prevent the formation of edema by two ways. One, the lymphatic system drains fluid away and then ultimately returns it to the bloodstream. And then the other way is plasma proteins help pull fluid back into the blood vessels, specifically at the end of the capillary. Okay, and it's important that we, in our pulmonary system, that we minimize this fluid loss, because that can lead to edema, which is bad. That'll increase the distance that oxygen has to travel and carbon dioxide has to travel. And it can also cause fluid to go under alveoli, which will cause the same thing. And so we minimize pressure doing one of two things. We can recruit more capillaries, and as we're going to talk about, I believe on the next video, we don't normally have all of our capillaries completely filled or used in our pulmonary system. We're efficient due to pressure gradients, zones of the lung that we talked about. Not all of our capillaries are being used all at once. And so we can go from recruiting maybe 50% of our capillaries to now 60, 70, 80, whatever the number is, depending on how much blood flow we've got. The other thing is that these capillaries can actually get a little bit bigger. So we call this distension. And so by distending, you could just think of it in terms of we're basically dilating them. And so if we dilate, we reduce resistance. And if we reduce resistance, then it requires less pressure to get blood through these capillaries. Okay, so we've got this figure here, and we've got a little bit of stuff going on. What I want you to look at is we've got our variables of pulmonary vascular resistance, pulmonary vascular pressure, and cardiac output. Now, if you remember, we've got this equation that is flow, so that's Q, equals pressure gradient divided by resistance. Okay. All right, so flow is our cardiac output, so there's flow. All right, we've got pressure here, but what we're mostly interested in is we're interested in the pressure gradient, which is going to be the difference between our pulmonary artery pressure and then our pulmonary wedge pressure. And you've likely never heard of pulmonary wedge pressure. Pulmonary wedge pressure is an approximation of left atrial pressure. Okay, it's it's easier to measure using this as the way I'm going to describe, as opposed to just putting a catheter in someone's left atria. Okay, so what they do to measure wedge pressure is they put a catheter in someone's vein, and they wind it through. They get it into the right atrium, right ventricle, pulmonary artery, and basically they keep threading that catheter until it can't go any further, and it gets wedged into the pulmonary capillaries, or maybe not quite that far, but close enough. And so that's why they call it pulmonary wedge pressure. This pressure approximates what's going on in the left atrium, left atrium. Okay, and so our gradient here is going to be pulmonary artery pressure, so PAP minus PWP. Okay. And so we divide this by what we call pulmonary vascular resistance, which is PVR. All right. Now, we can't measure resistance, and so we can calculate it. And so then what ends up happening is we go PVR equals, I'm just going to do delta P, so our pressure gradient, okay, divided by Q. And so if you take the difference between these two values, pulmonary artery pressure and pulmonary wedge pressure, okay, and you divide that by cardiac output, that gives you your resistance. Okay, and so notice as we go from exercise, we have relatively high resistance at the beginning of exercise. And actually, this is at rest, right? This is at resting values. But the more we exercise, the lower the resistance. Okay, and so what's happening here is the gradient's staying essentially the same. The pressure gradient staying essentially the same, but cardiac output is increasing. Okay, and so that's why we have this. It's not linear, at least not at the beginning, because there's a big drop. But this decrease in resistance allows for us to keep pulmonary pressures relatively low. And so with that pulmonary pressure, we're actually looking at the gradient between artery and left atria. Okay, and so we are able to minimize that pressure gradient by recruitment and distension. Okay, and I know this is a lot of new stuff or potentially new, so we'll definitely talk about this in class on Thursday.